This is Math 1100, Unit 4, Practice Exam B. All right. This is in the form of a fraction. Obviously, it's a quotient. We have the denominator. If we wanted to start with first trying to get this in the form of du over u, which is the natural log rule, if this were u, then du would be 8x to the third dx. Now, we have x to the third dx, but instead of an 8, we have a 40, and that's okay. Remember, if the coefficient's wrong, you can change the coefficient by moving it out here and multiplying by the coefficient that you need, as long as you also divide out there. So, this now becomes du over u, which is going to allow us to use the natural log rule. And then 40 divided by 8 is 5. So it's 5 times the integral of du over u. So then that turns into 5 times the natural log of the absolute value of u, which is 5 multiplied by the natural log of the absolute value, 2x to the fourth minus 1 plus c. Okay, for question 2, since we have a base e exponential, we could first try to use the rule that states the integral of e to the u du is just e to the u. If that doesn't work, we may have to use integration by parts. So we're going to at least try the e to the u rule. So we're going to let that exponent there equal u. So then du would be 20x to the fourth dx. And we have exactly what we need without having to multiply or divide by anything. We have 20x to the fourth for du, and then this could be e to the u. So this is a relatively straightforward problem. This becomes the integral of e to the u du, which is just e to the u. So it equals e to the 4x to the fifth minus 3 plus c. Okay, now we compare question 1 and question 3. They appear similar in that they're in the form of a fraction. There's no inside or outside function. So we may, like we did with question 1, try to get this in the form du over u and use the natural log rule. So if we let u equal x squared minus 3x minus 10, then du is 2x minus 3. Now here's the problem. There's no way we can change 4x minus 13 to be 2x minus 3 so that this can become du over u. So this method of trying to get the natural log rule isn't going to work. So what we need then is the partial fraction. We need to get the partial fractions for this expression. So this would be the lesson 6.2, where we do integration using partial fractions. So we're going to change 4x minus 13. We're going to factor the denominator into x minus 5 and x plus 2. So then the partial fraction would look like this, an a and a b partial fraction. And then if we multiplied both sides by the lowest common denominator, what we would end up with is 4x minus 13 equals a times x plus 2 plus b times x minus 5. Now we need to solve for a and b. But since we only have one equation, we need to cancel one of these values so that we can solve for the other one. So if I want to cancel a first to solve for b, I'm going to let x equal negative 2, because when I plug in a negative 2 here, a disappears. So 4 times negative 2 is negative 8. Negative 8 minus 13 is negative 21. And then here, negative 2 minus 5 is negative 7. B, so b is equal 2, 3. And then if we do it one more time to solve for a, we're going to let x equal 5 this time. If we let x equal 5, that's going to be 0 times b, so b disappears. 5 times 4 is 20, minus 13 is 7. And then 5 plus 2 is 7, times a is 7a, so a is equal to 1. So the partial fractions become 1 over x minus 5 and 3 for x plus 2. So we have 1 over x minus 5 plus 3 over x plus 2. So that's going to turn into two separate integration problems, the integral of this plus the integral of that. So we're going to have the integral of 1 over x minus 5 dx plus the integral. Now I'm going to move the 3 in front of this integral sign so that I can have a 1 as the numerator. So I'm going to move the 3 out front and call this 1 over x plus 2. The reason we're doing that now is that now we have, if this is u, x minus 5, then du, the derivative of x minus 5, is 1 dx. So this becomes du over u, which is natural log. Same thing here. If this is u, x plus 2, then the derivative of x plus 2 is 1 dx. So this is du over u, which is another natural log. So this turns into the natural log of the absolute value of x minus 5 plus the 3 coefficient times the natural log of the absolute value of x plus 2 plus c. For question 4, we have, even though it's in the form of a fraction like question 1 or question 3, you notice we have a function inside of another function with an exponent, which is usually an indication that we're going to use the general power rule with substitution. So if we let u equal the inside function, then the derivative so we have the x to the third dx, but what we're missing is the 20, where we have that 80. So like with question 1, I'm going to take the 80 out as a coefficient, multiply by 20, and divide by 20. So this now becomes 4 times the integral, and then I'm going to turn this into u, and then I want to move this whole expression up to the numerator to give this a negative exponent. So this is going to be u to the negative 5. And then this 20x to the third dx is going to be replaced with du. So then this is general power rule, where we have a something being raised to a power. So to integrate that, we add 1 to the exponent, and then divide. So then we replace u with 5x to the 4th minus 2 to the power of negative 4. Okay, for question 5, we have another situation where there's a function inside of another function that's the power. So it's likely that we can also do the general power rule on this problem. If we let u equal 5x to the 4th minus 1, then du is 20x to the 3rd dx. So we have the x to the 3rd dx, but it's supposed to be a 20 where that 80 is. So again, we can move the 80, multiply by a 20, and divide by a 20. So this turns into 4 times the integral of u to the 3/5, and then the 20x to the 3rd dx is going to get replaced with du. So this is pretty much identical to question 4. The power rule now applies. So we add 1 to the exponent. So if we add 5/5 to 3/5, it becomes 8/5. And then we multiply by 5/8. So then 5/8 times 4 is 20 over 8, or 5/2. Times u to the 8/5, which is 5/2 times 5x to the 4th minus 1 to the 3/5 plus c. Okay, for question 6, we have, similar to question 2, we have a situation where we have e raised to a power, so we may first want to try the e to the u rule. So if u is equal to 2x, then du would be equal to 2 dx. And here's the problem. We have this extra variable that we can't account for with any of this definition. So e to the u du isn't going to work. So the next option after that is integration by parts. And remember, integration by parts is u times v minus the integral of v times du. So we want to choose u and dv. So we wouldn't want to let u equal e to the 2x, because when you differentiate that, it doesn't become more simple. So we're going to let x equal u, so then du is 1 dx, and then dv is going to become e to the 2x. So to find v, if we've assigned dv, I'm going to veer off here. What we need to solve is the antiderivative of e to the 2x dx. What we would be missing is a 2 here, which means we need a 1/2 there. So the antiderivative of e to the 2x is actually 1/2 e to the 2x. Okay, so now we have u and v. And du and dv, we use the formula. U times v minus the integral of v, which is the 1/2 e to the 2x. I'm going to bring the 1/2 in front of the integral sign. That's v times du. And all that's left to do is the antiderivative of e to the 2x, which we already did over here. The antiderivative of e to the 2x is another 1/2 e to the 2x. So this integral of e to the 2x gets replaced with the antiderivative 1/2 e to the 2x. And then just multiply those two 1/2s together. So we have x times 1/2 e to the 2x minus 1/4 e to the 2x plus c. Question 7 is from section 5.4, definite integration using the fundamental theorem of calculus. So what we have here for this function, it's just a collection of individual terms. It's not a function inside of a function. There's no fraction to have to use du over u or e to the u. So the rule that applies is just find the antiderivative of each term separately. So the antiderivative of the first term is x cubed over 3. Here, this is going to turn into x squared divided by 2. So the 2 would divide the 8 into 4. So that would be 4x squared. And then 17 becomes 17x. And then what's left is to apply the fundamental theorem of calculus. So we input the upper limit of integration, -3, into the antiderivative first. So this is -3 cubed divided by 3 plus 4 times -3 squared plus 17 times -3. That's the antiderivative at the upper limit of integration. Now we do the lower limit, which was -6. So this is -6 plugged in for all the values of x. Okay, so this is -27 over 3. So that's negative 9. And then negative 3 squared is 9 times 4 is 36, minus 51. For the next one, negative 6 cubed divided by 3 is 72. Negative 72, rather. And then 36 times 4 is 144. And then 17 times 6 is negative 102. Okay, so then that first parenthesis is negative 24. Okay, and then this one, negative 72 plus 144 minus 102 is negative 30. And that's equal to 6. Okay, question 8 would be from section 5.5. We need to find the area of the region enclosed by these curves. Now these are both quadratic equations, so their graphs would be a parabola. They're both facing up, so what's most likely happening here is we have, maybe a situation like this. And we've got to find the area enclosed right there, perhaps. So next step would be, or first step rather, would be to find where is the intersection points of these graphs. To do that, remember we solve a system of equations. So 2x squared, this equation is set equal to the other equation. And then we solve a quadratic equation, get one side equal to 0. So I'm going to move all these terms over here. So that'll give us x squared plus 6x plus 5 equals 0. When we factor that, we get x equals negative 1 or negative 5. Those would be the bounds of or the limits of our integration. Next step would be to figure out between that interval, so from negative 5 to negative 1 in that interval, which function is the upper function, which one function is the lower function. So we do that by choosing a number in between here. So I can choose negative 2, plug negative 2 in, and see what the value of y is for each one. So here when x equals negative 2, y equals 0. For this one, when x equals negative 2, y is equal to 3. So this one has a larger value for y, so this is the upper function, this is the lower function. So when we set up the integration problem now, the limits of integration are from negative 5 to negative 1. We start with the upper function, subtract the lower function, and combine like terms. So we need to find the antiderivative of this function. Now it's not a function inside of another function, so this is just like number 7. We need to find the antiderivative of each term pretty much separately using the power rule. So it's going to be x to the third over 3. Here, if we increase to x squared divided by 2, the 6 divided by 2 is 3, so this would be 3x squared, and then a negative 5x. And now we can do the fundamental theorem of calculus. So again, we insert the upper bound first. Okay. Then we subtract the lower bound, or the value of the antiderivative at the lower bound. Okay, and then evaluate this. All right, so here we're going to have negative 1 to the third power is negative 1 multiplied by negative 1 is positive 1, so that stays 1/3. Negative 1 squared is 1 times negative 3 minus 3 plus 5. Here we're going to have negative 5 to the third power is negative 125, multiplied by negative 1 is positive 125. And then negative 5 squared is 25 times negative 3 is negative 75 plus 25. So from this we get 7/3. From the other one we get negative 25/3. Combine those together and we get 32/3. Question 9, this is an application problem from section 5.5. So we have consumer and producer surplus. So we've been given a demand function, which is linear. We've been given a supply function, which is linear. So we need to find the equilibrium point, which is the point of intersection of the two graphs. And then consumer surplus. So if we look at just a rough sketch here, the demand function, y-intercept is 200 and has a negative slope. The supply function, y-intercept is 50, has a positive slope. So the intercept there at the equilibrium, okay, this is the number of units, and this value here is price. So to find the equilibrium point, we solve a system of equations where we set supply and demand equal to each other. So here we get x equals 100. That's number of units. So to figure out the price at 100 units, we plug it into either one of these supply or demand function. If we plug it into demand function, we're going to get price equals $180. So that's equilibrium. Now the consumer surplus is the area underneath the demand function, but above this horizontal line representing the price. So that's this area right here. Now since it is the area under a curve, we could use calculus to find that area. However, the shape it forms is a triangle, so it'll be much quicker in this case because the demand function is linear. Just to consider the shape of that triangle. So this horizontal distance from here to here is 100. So that's that side of the triangle. From here, 180 up to 200 is a distance of 20. So the area is 1/2 base times height. So it's 50 times 20. 1/2 of 100 is 50. So that's $1,000. That's the consumer surplus. Producer surplus would be the area underneath the horizontal line of price equilibrium and above the supply function. So it'd be this area. This area right here. So that can be represented with, again, another triangle, only because the demand function, the supply function rather, is linear. The distance from here to here is 100, and then from 50 to 180 is 130. So that area is 1/2 of 100 times 130. So that's 50 multiplied by 130, which is $6,500. Okay, Question number 10 is from section 6.4, improper integral. The upper bound is infinity, so that's the one that needs to be changed by turning this into a limit problem. So we turn it into the limit as b approaches infinity, and now this upper bound of integration that was infinite is going to turn into this letter that you've described here. So I'm going to go from 1 to b of x to the negative 1/4 dx. Okay, so now we need to find the antiderivative of x to the negative 1/4. So that's just the power rule. So the antiderivative, if we add 1 or 4/4 to that, we get 3/4. Multiply it by 4/3, and then we evaluate that from 1 to b. And once we have that value, then we put a limit on it. So the antiderivative at the upper bound is 4/3 times b to the 3/4. Then we subtract the antiderivative at the lower bound, which is 4/3 times 1 to the 3/4. Okay, so here 1 to the 3/4 power is 1. 1 times 4/3 is 4/3. And then 4/3 b to the 3/4. This is now going to be evaluated as a limit as b approaches infinity. So what's happening here is this value b is getting larger and larger. Okay, so we have an increasing value of b that's being raised to a power. So what's going to happen is this value is going to continue to increase because b increases, you raise it to a power, makes it even bigger, you multiply by 4/3, makes that even bigger. So this increases without bound. So it's an ever-increasing number, and if you subtract 4/3 from that, it still gets bigger and bigger and bigger. It's not heading towards any particular value, like in some we've seen where it tends towards 0, which is a number we can use to compute. But this isn't tending towards any number in particular, it's just increasing without bound. That kind of behavior we call diverge, so it diverges, and is the answer you would leave for that one.